All right, so this is part two of the thermodynamics lecture. So we're going to pick up on slide 21 and we're going to go all the way through the end. Now, this video is not going to work any practice problems or not any major practice problems. Make sure that you watch the practice problem video to kind of see some things that we're going to talk about here in action. So we've talked about the first and the second law of thermo. Let's look at the third law. So the entropy of a pure crystalline substance at absolute zero, and we're talking about absolute zero Kelvin there, has to be zero. That's kind of a by definition sort of thing. If you wanted to see that kind of worked out, you can see it right here, right? Entropy equals Boltzmann's constant times the natural log of the number of microstates. Well, if you have 0 degrees Kelvin, and we know that Kelvin measures molecular movement, then at 0 Kelvin, there would be no molecular movement, so there'd only be one microstate. The natural log of 1 is going to come out and kind of ruin that calculation because the natural log of 1 is 0, so K times 0 is 0, which would mean entropy is 0. Now, when we start to examine a graph of entropy and temperature plotted against each other, the thing that we notice is that as temperature increases, entropy seems to increase, and that matches what we talked about with the second law. Notice that on the phase change borders, where there's melting or boiling here, the temperature is not increasing, but the entropy definitely is, right? So there is some delta S in there. Now, your textbook on table 19.1 has some molar entropies at 298 Kelvin. That's the number that we use for our reference values. We don't use 0 Kelvin because otherwise all of your reference entropies would be 0, and that wouldn't do us any good. So when we look at standard molar entropies, keep in mind, just when you do your calculations, you're looking at 298 Kelvin for a temperature. All of the standard molar entropies for gases follow a general trend of being greater than liquids and solids of the same species, but as the size of the gas molecule gets bigger, that can be a little bit misleading, so just keep that in mind. Pretty much all of the standard entropies are going to increase with mass, and they're all going to increase with the number of atoms in the formula. Remember, the more microstates that are present, the greater the entropy is going to have to be mathematically. Now, when we look at entropy change, we calculate it just like we did in chapter 5 for delta H, right, with our change in enthalpies. So our formula looks identical with the exception of the fact that we're changing the H for an S. So the sum of the changes in entropies for the products minus the sum of the changes in entropies for the reactants. Don't forget to plug in your coefficients from the balanced equation for N and M here in order to find the overall delta S. Now, if we're looking for entropy changes in the surroundings, so this would be more for our system, this is going to be for our surroundings, then we're looking for a change in heat, because as heat changes, so is entropy. So we use delta S of surroundings equals negative Q of the system divided by absolute temperature in order to do that. This is for isothermal processes, all right? So it's probably an important term you want to get familiar with. And we do these calculations at constant pressure, or we set up our experiments to be constant pressure to make it a little easier on us. And at constant pressure, it's important to know that Q of the system is going to equal the enthalpy of the system. There we go. So we can sub this in for our equation. Remember, we can usually get those from Hess's law or from a table, depending on what we're trying to calculate. If we want to look at entropy change in the universe as a whole, then we have to examine both the system and its surroundings. Remember that if you have a spontaneous process, the entropy of the universe must increase. And so that brings us back to spontaneity, which we talked to in the first video. So if the delta S of the universe is equal to the change in the entropy of the system plus the change in the entropy of the surroundings, and we take what we know about the surroundings and we substitute in delta H of the system divided by T, right, the thing we just looked about, and we move T to the other side, so we multiply by negative T, because that's going to get rid of this little negative sign right there. That tells us that negative T delta S of the universe equals negative T delta S of the system plus the enthalpy of the system. We can rearrange that to get delta H minus T delta S, and that's going to bring us something new. Negative T delta S of the universe is called Gibbs free energy, which we abbreviate with a capital G. And this formula right here is how we calculate Gibbs free energy. And Gibbs free energy is going to tell us whether or not a reaction will occur spontaneously in a certain direction. You definitely want to memorize this equation. So delta G equals delta H minus T delta S. Now, if delta G is a negative number, then our reaction is going to be spontaneous in the forward direction. If delta G is 0 when you calculate it, then our system is at equilibrium, and so we would expect the reaction rate to be moving in the same direction, or at the same rate in both directions. Remember, there's no such thing as a static, or there's really not a static equilibrium that we're going to reach. If you get a positive number for delta G, then the reaction is spontaneous in the reverse direction of however you've written it. Okay, so it will proceed in the opposite direction unless you force it not to. Now, when we look at standard free energy changes, we're basically going to look at those in the same terms as we did standard enthalpies of formation. So instead of the H, we're putting a G in there, but this is analogous to delta HF prime. Okay, so we're going to put the little analogous sign there. You're still going to see N and M as your stoichiometric coefficients, and everything about that is going to be the same. Now, when you look at free energy changes, this table right here is absolutely vital that you know. You don't need to memorize the example, but I would just encourage you to commit this table to memory, all right, however you need to do that. Questions that you're going to be asked that this will help or help you answer. How does delta G change with temperature? Okay, that's the big one. If you understand this table, and you'll see this when I work the practice problems in the video, this table will help us answer some questions like that. But that's going to be the most common one. Since your reactions are going to be spontaneous when delta G is less than 0, right, when it's negative, the sign of enthalpy and entropy and the magnitude of the temperature is going to all matter to spontaneity, because, if I have a negative enthalpy, right, and I end up with, a positive entropy change, all right, well, my negative T delta S, because it's negative T times a positive, this whole thing is going to end up as a negative. So if I have a negative enthalpy and a positive entropy, then I can expect that to be a negative delta G, and I'm going to have a spontaneous reaction at all temperatures. That's the first line here of this table, right? Negative delta H, positive delta S, that gives me a negative delta G. On the other hand, if I have a positive enthalpy and a negative entropy, then I can expect that to be non-spontaneous at all temperatures, because I'm going to have a positive delta G. So make sure you kind of work your brain through this table, and we'll see it again when I work some of those practice problems. Now, even if you work under non-standard conditions, and what we've been talking to so far has been under standard conditions, the free energy is still going to be found with a mathematical equation. Under standard conditions, you have 1 molar solutions. Q is going to be equal to 1, and ln of Q is going to be 0. And so this RT ln of Q thing is going to cancel out. Under non-standard conditions, though, that's going to be important to include. We'll look more at Q and K when we talk about equilibrium. But what you need to know for now is this. At equilibrium, Q is equal to K, and delta G is therefore equal to 0. The equation then looks like this. 0 equals delta G plus RT ln of K, And when you solve that to find K, you have to use E in order to get rid of your natural logarithm. Again, hopefully you learned that in algebra. So this little equation right here is going to be useful to know. I believe it's on the constant sheet that you have, but just in case, I would jot it down. Now, I know that's a pretty quick look at those last 10 slides. As far as the math is concerned with this, you're going to want to watch the practice problem video for chapter 19, in which case we will go through some actual step-by-step solving. If you have any questions, let me know, and I'll see you guys in that video.